All right, Master of Science students, sorry, let me lock this door to my research laboratory. Uh, Welcome to this session on the remaining items related to the kinetics. And then I think we'll start on later this topic on structure activity relationship. So there are two things which I need to mention, uh, which are in the course outline and we have not covered earlier. And the first one is on the Hammond postulate, and the other one is on the Curtin Hammett principle. As you can see, there are two words here. There is a postulate here. Can you see well? I believe now the camera is a bit close. There's a postulate, there's a word postulate here, and then there is a principle. Yeah. So I think by now you know the difference between a postulate, uh, which you try to explain what is actually happening for something that has not yet been actually been proven or really what do you call it, agrees with the experimental facts in which it becomes a theory. Yeah? So you know there's a difference between a postulate uh, and a theory. Yeah? A theory is one in which, based on certain assumptions and everything, it agrees with the experimental data, and as such, you can be able to use it for predicting some events or some uh, uh, something happening in the physical world which may not have been encountered, but it's based on the theory or an equation which you have formulated, which makes use of certain assumptions. That's like a theory, yeah. So in this case, you're talking about a postulate, and this relates to the transition state. Most of these things we are talking about, they relate to the transition state, yeah. So what is a transition state? Transition state, or in some in some books, you may see it being called a transitional structure. Transition state, transition structure. So it is the most unstable structure or system uh, that exists in a transformation uh, from the starting material to the product. Yeah. So there is something like a like a barrier hill that must be climbed before uh, before the starting material changes to either an intermediate and then eventually to the product. So this highest product is being shown if you're going to have something like orbital interaction. You are showing it in such a way that the orbitals between one maybe if it's an s orbital and the p orbital, the orbitals are just touching. So it's just being shown if you are just having like a structure like A and B. In this case, you're just showing dashboard. So you can say there are bonds that are partially forming and others are partially breaking, as opposed to these are, for example, these are complete bonds, yeah, like the ones which are straight. So the ones which are dashed, you're saying these bonds are partially forming and others are partially closing. So in this case, this is not it's not a stable bond, yeah. A bond is the optimum distance that optimizes the repulsion and the attraction of electrons. Yeah. So there is the optimum distance uh, between between one nuclear and another, between one atom and another one in a bond. But by now you know uh, there are two major types of bonds, though there are some inner categories. There is the ionic bond in which the polarity between the atoms coming together, for example, like between sodium and chlorine. Sodium is very much electropositive, chlorine is electronegative. So because of the large electronegativity difference, the bond between them is electrostatic, so it is ionic. as opposed to between carbon and hydrogen, which have got almost the same electronegativity difference. So the bond is said to be nonpolar. But once again, you're going to see there are some other categories, like there can be a polar covalent bond, like in water, whereby uh, there are atoms which are much more electronegative, but not to the point of reaching the ionic state. So you are going to put the word delta plus and delta minus. I believe you know those distant those distinctions, and therefore I'll not go into those. Yeah, yeah. So the transition state is the most unstable structure that exists, and it it cannot be isolated, for example, or you cannot be able to actually photograph. What am I saying about photography? What you're going to see is that uh, a lot of changes have taken place in that. For example, it is possible to photograph atoms. Yeah, uh, if you're going to Google the photographs of atoms and even molecules, especially atoms, you can be able to see the current photographs of that one. So, and also, it is also possible uh, using some very fast photography in the something called I'm using this word femtosecond. That is 10 to power minus 15 of a second. Yeah, that's a very short period. Huh? So it's like making use of flashes of light, taking photos very fast. So you can be able to see exactly what is happening in a combustion or something. So you can be able to see exactly, like if you have something like an explosion, yeah, you can be able to see uh, bit by bit as to what happens up to when there is the actual explosion or whatever. It's like a movie in which you can stop frame by frame. Yeah. So there are those cameras which have been developed to be able to now see those very fast reactions that are taking place. But it's not possible to photograph or maybe to be able to identify the transition state. So with the transition state, you can only postulate this is what is actually happening, but you cannot be able to isolate a transition state. So in this case, you've got a scientist by the name of Hammond who postulated this what is likely to happen, and in this case, is saying, hey, um, uh, and this based on the fact that uh, using the equation that we saw from that from the rate equation, I mean from the rate constant uh, and the temperature, you can be able to determine the activation energy. Yeah? You you remember about that one. You can be able to determine if you know the rate constant of a reaction at the temperature at which it's taking place. Excuse me, in Kelvin, you can be able to know the activation energy. So in this case, you can be able to know the barrier. So in this case, it's saying, hey, uh, some reactions they they go to the transition state quickly and some go to the transition state later. Yeah, there are some which go to the transition state immediately, and then the dissipation of energy to the ground state or to the product takes long. As opposed to in this case, it takes long before you actually get a transition state, and then finally you get a very quick transition state leading to the product. So in this case, what can you say? This is said to be like an early transition state. It because it's very closer to the starting material, and this is a late transition state, meaning that it's very close to the product. So this is a late transition state. This is an early transition state. And what this postulate is saying is that if you're going to have an early transition state, yeah, then then that transition state should resemble in a way, the structure of the reactants. Uh, in chemical reactions, there's a difference between the starting materials and the products. But what you're going to see later in some reactions which are going to be calling pericyclic reactions, where there is no intermediate, there's a relationship between the starting materials and the product, and therefore the structure of the starting material determines the products, and therefore you're simply going to look at the overlap of the orbitals in the starting materials, and then you can be able to predict exactly the kind of product that you're going to get. But in the normal ionic reactions which go through ions which can rearrange and everything, there may not be a lot of difference, there may not be a lot of relationship between the starting material and the product. So in this case, it's saying in a net transition state, in a net transition state, it actually resembles the product, as opposed to an early transition state, it resembles what? The starting material. Once again, it's a postulate because you cannot be able to actually photograph or isolate what? A transition state, to be able to know exactly this is the structure of the transition state. Once again, from that one, for the activation energy, excuse me, based on the rate constant and the temperature, you can be able to know the height of this barrier, which is the activation energy. Yeah? So you can be able to know this high activation energy, this low activation energy. Now, what you're talking about is going to lead to the next thing, which you're going to be calling a principle. Yeah. Think of a principle in nature. Maybe you've been told something by a motivation speaker. This is a principle. If you do this, this is what's going to happen. It means that you take it or leave it. You understand? So that is a fact that has been observed, and no matter what you do, you cannot change it. You just accept that one as a principle. So in this case, it's telling you this principle which was observed by these two gentlemen who are called Curtin and Hammett. Later, we're going to get to what Hammett plots later. But there's this Curtin Hammett principle, which is quite interesting because most of the people are just saying, hey, you've got you've got an intermediate. So if you've got an intermediate, if you're just going to let it probably go to the product or to the starting material, then the most stable or the thermodynamically most stable should form in larger quantities. Yeah. And the one which is going to be thermodynamically less stable is going to be formed in lesser quantity. Yeah. That's what has been happening. Sometimes you leave intermediates there, the equilibrium, then eventually you're going to form um, the most stable should actually be the one forming. Excuse me. It's going to form um, uh, should actually form in larger quantities. But what has been observed, and this is what you're going to see, is a bit interesting. And that's why this diagram is shown here. What can you see here? I believe, yes, it can be seen correctly. There is the energy, and you know the higher the energy, the less stable it is, the lower it is, the more stable it is. So there is the energy here, and then there is the progress of the reaction here. What can you see? There is an intermediate B, then there is a product C, and then there is a reactant A. Can you see one? Intermediate B, then there is a reactant A, and then there is a product C. What can you see? Probably B has got a certain energy which I'm going to call probably maybe X. Okay? And then what can you see here? There is a large activation barrier here, activation energy, to give a product C, which is thermodynamically more stable. And then there is a smaller hill here, which is giving the reactant A, which is thermodynamically less stable. So naturally thinking would say, hey, This is thermodynamically more stable, and therefore I should form, if B is allowed to react or to equilibrate, then what I'm going to get is a lot of C and almost nothing of A. But what this principle is saying, the product ratio or the reactant and the product ratio is not determined by their relative stability or how quick they can form or whatever, but by the ratio of the activation energy. If you are going to have a smaller activation hill or the activation energy to be overcome, then even if this one will be less stable, it will be formed in larger quantity than this one, which is more stable, but it has a higher activation energy, activation hill to be climbed. It is crazy, but that's how it is. It doesn't matter about thermodynamic stability. It doesn't matter about all those kind of things about this thing forms quickly or not. What determines is the barrier to be overcome. Yeah. So this one will get less energy from the environment, and therefore, even if it is unstable, but there is a small hill to be overcome. This one, even if it is more stable, but there is a larger hill to be overcome, and therefore, if you're going to see the ratios, you're going to see A will be formed in larger quantity as opposed to C if you are starting with this one. Yeah. So that's called the Curtin Hammett principle. And once again, it's a principle. It's like take it or leave it. Yeah. Um, it throws into spin all these things about thermodynamic stability, and therefore this thing is going to be formed in larger quantities and everything, all those kind of things. So, so what matters is the hill to be overcome, that activation energy hill that will determine what the product or the ratio between what's going to be formed. It will be determined by this hill, irrespective of the stability of whatever is being formed. Are we together? So that is the Curtin Hammett principle. Okay. Now, let's now begin on this last major topic before we look at the introduction to the molecular orbital theory, and then really focus on the pericyclic reactions. Now, as it's written here, there is the structure. Can you see well? Yes, structure activity relationship. Structure activity relationship. Now, what can you see here? There is a carbon here, there is another carbon here, and then we are looking at a functional group. A functional group is either an atom or a group of atoms, which gives the molecule its functionality. So that if I'm talking about a carboxylic acid, then the ease in which that carboxylic acid loses a proton, that will make it either a strong or a weak acid. So that is the functional group. Or in this case, you can be talking about what? Something like an aldehyde, or what? Or an alcohol, or an what? Uh, Alkyl halide and the rest. So that's the functional group. Yeah. Are we together? Now, along the carbon there is a group B, and then there is a group A. Yeah. In this case, B is closer to the functional group because it is on there this notation. So this is called alpha carbon, and this is called beta carbon. So the B is on the alpha carbon, and atom A is on the beta carbon. Yeah. So in this case, by inductively, you're talking about field effects that that in either donating electrons or withdrawing electrons, whatever it is, the group which is nearest to the functional group is going to have greater influence. Electron donating or electron withdrawing group. By this time, you're going to hear some words like electron withdrawing group or electron donating group. Yeah, you're going to hear words such as those words. Yeah, excuse me. Okay, you're going to hear those words like an electron donating group or an electron withdrawing group. So the closer it is to the functional group, the more its influence. Or even steric. By steric, it means how bulky it is. The closer it is, the more it's going to influence. It's going to influence the functional group. The closer it is, the more it's going to influence. So the atom A, it is further away than B from the functional group. So the influence of A is going to be much less than for B inductively. Yeah? So later we're going to see uh, uh, inductive effects in terms of the molecular orbital theory in terms of the overlap of the orbitals, that there is something more to the inductive than just saying, hey, maybe like I've got an alkyl group like a methyl group. If they are going to have many methyl groups, they're going to be pumping electrons to a carbocation, something like that one. You're going to say, hey, but how is a methyl group pumping electrons? Yeah, uh, and it has the same electronegativity as the carbon bearing the carbocation. Have you asked such kind of things? So later you're going to see what exactly is this pumping electrons using molecular orbital theory. Yeah, you're going to see exactly what that inductive effect, something called hyperconjugation, and the rest, how it affects the electron density, something like that. Yeah. So inductively, we are saying that B has got more influence on the functional group than A. So FG means functional group. Yeah. EWG is an electron withdrawing group. Is an electron donating group for EDG. Yeah, electron donating group. Yeah. Now that is inductive effects. Now, when you're dealing with conjugation, by conjugation it means you've got a double bond separated by a single bond, and then there's a double bond separated by a single bond, a double bond separated by a single bond, a double bond, something like that. Now, in this case, we are saying in a, what is this word here? In a pi system, distance does not matter provided you have a conjugated system. What I'm saying is this: if you have such a system, is that this pi bond can overlap like this. Immediately, this one overlaps like that. This one transfers electrons, and this one transfers electrons to the carbon bearing the functional group. So when you're dealing with conjugation, the distance does not matter. Now this thing becomes very clear when you're dealing with colored compounds where there are so many functional groups. Uh, uh, so conjugation does not depend on the distance. You're not going to say, this is a closer conjugation system this far. Provided it is a conjugated system, electron can move from whatever the end of the conjugated system and transfer electrons to where the functional group is. Yeah. So when you're dealing with a conjugated system, the distance does not matter. But in inductive effects, the distance matters. Have you noted it down? In inductive effects, the distance matters. But in pi systems which are conjugated, the distance that does not matter. So the transfer of of electron density can be transferred effectively across the conjugated system. Yeah. So so in this case, okay. So I think what I'll do is that I'll take a pause there, and then I think we look at how this structural activity relationship can apply to some systems that will lead us to look at this thing called the Hammond Postulate. So in this case, we'll just refresh our knowledge on the aromatic compounds. Yeah. Um, the reason why we're going to be focusing on this is that is that the normal chain can actually bend and move, and that can affect the rigidity of the structure. Yeah, it can affect the rigidity of the structure, especially when you've got a single bond. It can actually move like this one. Like in this case, you can say, in this case, probably B is closer to A, but if it bends, for example, if it bends after some time, A can be closer to the functional group if the molecule is actually going to actually bend. Yeah, if you're having a single bond. And in such a case, you're going to see that A may become closer to B. In this case, we're saying if this structure is linear and does not change, then A is going to be further away from B. But if you're going to have those steric effects and steric hinders and the rest, then if you're not going to have a rigid structure, then uh, then it may be hard to actually say uh, permanently that A will have less influence on the functional group than B. So we want to look at systems which are going to be said to be rigid, and you're going to see some very interesting facts about structure and activity. So so in this case later we're going to be looking at, um, uh, at these structures which are going to be based on benzoic acid. Benzoic acid has got a benzene ring, and then next to it there is the carboxylic acid. Yeah, it's called benzoic acid. So we'll be looking at benzoic acid and similar structure and see how this rigid system can actually tell us something about the activity. In this case, uh, these are the systems which are chosen by this somebody called Hammett, and you're going to be looking at what what he developed from that one, based on the rigid system. So so in a short while, you're going to stop looking at the aliphatic groups and groups which can actually bend, and you're just going to be focusing on rigid systems, and then we see there's some very important information which you can gather about structure activity, yet something about mechanism which you can gather from looking at rigid systems. So we are going to stop there, and then in a short time we'll now look at aromatic systems. Yeah, and the information they can tell us about reactivity. Yeah, okay. I believe everything is okay. I think the board, I think, is much closer. Initially, I'd put the camera back, but it appears as if the distance which you put really matters. But I believe now everything is quite clear. So we'll stop there, and then I think we'll proceed looking at aromatic systems and something about structure activity relationship. Yeah. Okay.